Hello. Uh, this will be a recording on Lorentz transformation, and just for reference, the date today is March. Let me undo this. March 23rd. And this is a lecture I'm recording for Physics 420 SIU. So today we want to talk about Lorentz transformation and how it can be motivated from Maxwell's equation. So it's Lorentz transformation. And let me erase this off. We have seen that Maxwell's equation implies a wave equation for the electric and magnetic field. Let me write that down. Maxwell's equation imply wave equations, so which are written as gradient square minus 1 over the speed of light shows up here, and the partial derivative with time square. And this could be the electric field or the magnetic field. That's equal to 0. C here is given in terms of the property of the vacuum, epsilon naught and mu naught. This is the permittivity of the vacuum and permeability of the vacuum. Basically, how much can you polarize a vacuum? So we are talking about the polarization density of the vacuum and permeability density of the vacuum. And that led to the idea that maybe vacuum itself is a medium, and that was called ether in those in early days. But in 1885, 1885, Michelson-Morley experiments uh, uh, suggested no ether. That means to say that the perspective that the the medium through which light is going, or what we call vacuum today, is not really a medium, and speed of light seems to be an absolute constant with respect to every frame. That led Einstein to suggest that suggest the relativity idea, and what that says is that light, when seen by two different observers that are moving with respect to each other, look exactly the same. So let's look at a spherical wavefront. So spherical wave of light. So what does that mean? So what we are saying is that there is a point down here, and as time evolves, there is a spherical wave that emerges out and travels farther and farther. And this distance that the light travels in a certain amount of time satisfies the equation of a sphere, and that is x square plus y square plus z square, presuming that it started from the origin, is equal to the radius of the sphere, and that is also equal to the amount of time light takes to travel from the origin all the way to the surface of the sphere. And using the speed of light formula, we'll have that distance to be c square times t square. Right? So that's how an observer sitting at the origin would see the light traveling outward from the center. But now let's think of an observer, another observer, who is moving with a velocity v away from the center. And he or she will also see a light source radiating outward, and one would have expected that this outward source need not be spherical, because this will be deformed when one of them is moving relative to other. But experiments of 1885 suggested that that's not the case. This observer has to also see exactly the same same equation. So that's the idea of relativity. So the x prime square plus y prime square plus z prime square, and they observe, they might be measuring different distances, different times, but the idea that light travels at the speed of light and thus goes in exact circles or spheres in this case, has to be the same in both observers. And that quantity is related to v, and this has to be encoded, or we would like, or the idea or the question we can ask is, what is the connection between x prime and x? Like how are the space times as seen by the observer at the origin of the first sphere related to the observer who is sitting on the at the center of the moving sphere, as pictured in this diagram. To that end, one one says that this means that we have the relation x square. One could say, if this is true, we should have, since x square plus y square plus z square minus c square, t square has to be equal to 0, and the same thing is true for the other observer. So there must be a relation, and presuming that relation is constant, or let's choose that to be identity here. So this is equal to x prime square plus y prime square plus z prime square minus c square t prime square. And our Lorentz transformation is the answer to the question, what's the connection between x prime and y, all the primed variables and the unprimed variables. You go with the ansatz, or we presume that x prime and y prime remain the same, that the motion be in the z direction. So this remains the same. Y prime also remains the same, but we allow c prime to be related to z and time altogether. So that's a times Z plus B times, we can say B times T, that will be making it linear, but then A and B will have different dimensions. So just for the making the dimensions of A and B the same, we introduce a C here. So that C times T has a unit of distance, and then in that case, A and B have the same dimension. Similarly, we say C times T prime is equal to C times Z plus D times T. We have assumed linearity, linear relations between the primed and unprimed variables. We assume linear relation. And when this was argued for the first time, to my knowledge, by Einstein, it was pretty much argued that since space and time is homogeneous, and the way we look at around us, it has to be translationally symmetric, it has to be isotropic. He used a lot of symmetry arguments to motivate that this should be linear. But even otherwise, we can say that at least we get one solution in this sense. That's another way of looking at it. Either way, our goal is to find out what's the connection between the primed and unprimed, and what can we say about ABCD if the above equation has to be true. So we substitute it back in the equation, and it's very clear that we get the equation says that this is x square plus y square plus z square minus c square t square is equal to x prime square y prime square, or or actually let me erase this a little bit. Since x prime is equal to x, it is immediately satisfied. We don't have to write that. This is minus c square t square, and z prime is a times z plus b times c times t square minus of c times t prime, the whole square would be c z plus. That has to be true, and we can simplify this further. There is we can collect the coefficients of z square, and next we have the coefficients of ct square, and let me write it as minus of d square minus b square times c square t square, and the cross terms plus 2 times z c t, and the coefficients for that are ab minus cd. And it's very clear that if this equation has to be satisfied, the coefficients of z square on the right hand side has to be equal to the coefficients of the appropriate terms on the left hand side. This implies, right, then we get some relations. This implies that a square minus c square has to be equal to 1. D square minus b square has to be equal to 1, and AB has to be, AB minus CD has to be equal to 0 because there is no corresponding term on the left hand side. So we have AB is equal to CD. So that's 4 unknowns and three equations, so we cannot expect it to completely be determined, but we can at least bring it down to one coefficient. So let's quickly see that if we start from the first equation and substitute the third equation in it, so we have a square minus c square will be a times b over d, right? Square, that's equal to 1, but then d square minus b square anyway is 1, so this implies that a square what did I say? So this will be a square so I substituted c to be a times b over d, so we get a square is equal to 1 from this, because d square minus b square is uh, is is 1. Correct. No, that's not what I would have expected to come out of this. So let's see, a square c is a times b over d. So it's a square, and then d square minus b square is 1. So I do get a square equal to 1. And that would mean c is equal to 0. This is not correct. What's going on? Help, 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 help. So a square minus c square minus d square minus b square, that's correct. And 2 times ab c times ct minus that ab minus cd. Okay, so a square minus c. C is a times b over d. What's going wrong here? Let me let me see. So I need help here. Oh no, that's not correct. So that's not the way you conclude that. So where's the eraser? Sorry. Yeah. So okay, I was doing things wrongly in my head. So if I were to simplify this, I get a square d square minus b square is equal to d square, and this leads to the relation a square is equal to d square. Same thing, I can start with d square minus b square equal to 1 and substitute d this time, so you get d minus cd over a square is equal to 1, and you get d square is equal to a square. So this leads to again the relation that d square is equal to a square, which also implies that if I substitute d is equal to a in the ab is equal to cd relation, this also implies that b square is equal to c square. So it seems like we have the, let's choose a and d to be of the same sign. So a is equal to d and b is equal to c. And that's the best we can get uh, A is equal to D and B is equal to C, and we finally have A square minus C square is equal to 1. And what's the relation that leads to this equation? The proposition is that, as I said, we cannot derive this to a certain extent, because to a complete extent, because there are only 3 equations. So this reminds us of geometry. Trigonometry, remember, involves cosine square theta plus sine square theta equal to 1. But there is a very similar situation we can have in terms of hyperbolic constants. If we were to say A is equal to cosine hyperbolic theta, some parameter theta, and C is equal to sine hyperbolic theta, then that's a valid relation. So then we have A square minus C square satisfied. But if that is indeed the case, then we also have C and D known, and which immediately gives us our transformation, with the caveat that what this angle theta is. So within the parameter theta, we have the Lorentz transformation to be given by Z prime is equal to cosine hyperbolic theta times Z plus sine hyperbolic theta times C times T, and C times T prime is equal to sine hyperbolic theta times C plus cosine hyperbolic theta times C times T. So that's our Lorentz transformation in terms of the angle theta, but we still have to see a connection between V and velocity, V, the relative velocity between the two observers, and the angle theta. With that thing remaining, we have, let me rewrite the relation we wrote down. It is, while I'm rewriting it, the relation that I wrote down just now can also be written as Z prime C T prime as a matrix transformation, and that has this nice symmetry property that that you can write the transformation as if it was acting on the vector formed by the variables Z, the space and time. Of course, this corresponds to Z prime is equal to cosine hyperbolic theta times C plus sine hyperbolic theta C times T, and the transformed time is related by sine hyperbolic theta times Z plus cosine hyperbolic theta times C times T. But we haven't said anything about the angle theta, and this is where we make a connection with the experiments or the physical problem in mind. This, if not anything, we can say is based on experiment. We so physical experiments physics implies that we say tangent hyperbolic, not the sine and sine, tangent hyperbolic theta is defined at this stage to be the ratio of the velocity of the relative velocity of the two observers or the ratio of the relative velocity of the two observers with respect to the speed of light. So this is v here is relative velocity of observers that we talked about, the two observers that are measuring the motion of speed of light going away from the center with respect to each of them. So that's v over c. We will often denote this by the letter beta. So that's a notation, a very generic, very common notation in many of the textbook and many in the most of the modern literature, if you want. And if we use the idea of connection between in secant hyperbolic and tangent hyperbolic, we get, remember, 1 minus tangent hyperbolic square theta is equal to secant hyperbolic square theta, and secant is 1 over cosine. Right? That leads to the point that cosine hyperbolic theta, which is 1 over secant, so that will be 1 over 1 minus tangent hyperbolic theta square. Okay. Put a square root in there, and that leads to 1 over 1 minus v square over c square, or 1 minus beta square if you want. And this is defined to be a new parameter, gamma. Oops. Right, gamma. If cosine hyperbolic theta is gamma, then what is sine hyperbolic theta? So sine hyperbolic theta would be multiply and divide by cosine hyperbolic theta, and we get tangent hyperbolic theta times cosine hyperbolic theta, and that gives you beta times gamma. So that seems to suggest that the Lorentz transformation is z prime ct prime is equal to gamma times beta gamma beta and gamma c times c times t. And that's Lorentz transformations. This will play a central role in the next few weeks of what we discuss on special relativity. This was first derived by Lorentz in, I think, 1890, long time before Einstein, but the actual interpretation was completely different. They were trying to explain the existence of ether using this transformation, but it was Einstein who came and gave the interpretation of it to be the actual transformation of space and time variables. Notice that here beta, the variable beta here, which is v over c, is always less than 1, right? And this is this could be this has to be greater than or equal to 0. So we have beta less than 1 and greater than or equal to 0. In principle, it can even approach 1, so you can even say equal to 1, but that's assuming that light travels at that speed. So and gamma, right, gamma, which is equal to 1 over 1 minus beta square, is always going to be greater than 1. So gamma is always greater than 1. And also, what are the so in the next class or in the next video, we'll talk about the implications of this Lorentz transformations. So the implications, at least at a popular level, we will really talk about kinematics and dynamics very quickly. But it's while we're doing this, it's good to point out that Lorentz transformations suggest that space or spatial distances contracts length as such contracts. Time dilates. And velocity addition formula is no more that of Galileo. Instead, we have the Einsteinian velocity addition, the Poincare addition formula. And we would also like to have a geometric interpretation of why does these things happen, and what is or we will try to accept it as it is completely fine, because in this transformation it is the components that are changes. Length and time in itself are not the interesting things that should be compared with. What two experimentalists or two people who make measurements should compare is quantities or quantities which are invariant. For example, when you make a rotation, you don't talk about, oh, the x component of my vector doesn't match with another observer. It is the length of the vector you match with. So those are the things we will talk about. But for that, we'll come back and make a separate video. So let me stop this video here. And for that, let's see. And next time we will talk about these implications. So stop recording. Bye-bye.